Hello. Now we're going to continue our work in algebra and we are going to be looking at indices today. Now indices are things we've been dealing with right since first year. We have indices, we've also called them the powers on numbers and we've called them exponents, and they all mean the same thing. And anytime we're going to be dealing with these indices, anytime we see complicated stuff involving powers, we're immediately going to open up page 21 in our log tables. And this is key to our skills that we're going to be developing this year. Log tables have to be with us all the time, and anytime we can see an opportunity to use them, we want to be opening up our log tables and checking so that by the time we get to our exams, this is total muscle memory. I know where I'm going in the log tables, I know what I'm going to see, and I have them there for reference. This is a really important skill, and we need our log tables in class and to work with all the time. Now, back to our indices. I'm going to start off by talking you through a few basic examples of what an indice or a power is. So if I have 2 to the power of 4, what does that mean? It means I've multiplied 2 by itself 4 times. 1, 2, 3, 4. I've multiplied 2 by itself 4 times. And if I take something like 3 cubed, what does that mean? It means I've multiplied 3 by itself 3 times, and I end up with 27. Now that's powers on numbers. The other thing that we've come across quite a lot is square roots. So in the minus b formula, or in lots of different situations in algebra, we've come across the idea of a square root. Well, what does a square root mean? If I have a square root of 36, it's asking me a question. It's effectively asking me the reverse of the question I'm asking myself here. How many times do I multiply a number by itself? It's with a square root, it's how many times what number do I multiply by itself to end up with 36? What number must I multiply by itself to end up with 36? Well, I know that 6 squared is equal to 36. So if I multiply 6 by itself, I get 36. So what number must I multiply by itself to get 36? 6. So this is how our square roots work. They're the inverse, they're the opposite, they're what undoes or the opposite or the inverse of a power on a number. And because of that, we actually write them, the powers effectively, as an inverse. So a square root, so a square of a number is a power of 2. A square root of a number would be 36 to the power of a half. We effectively flipped the power of 2 upside down. We inverted it. So that is how we would write a square root as a power or as an indice. And we can also have things like cube roots. If I go back to 27, and I put a little 3 there, that means the cube root of 27. What number must I multiply by itself 3 times in order to end up with the number 27? 3. I must multiply 3 by itself 3 times in order to end up with 27. And the way that we would write that is 27 to the power of a third. So it's the inverse, it's the opposite, as we might expect from what it is we're doing. We're doing the opposite direction than what we did when we had our simple powers. So that's powers and roots. And we've already dealt with them. We already actually know them. And hopefully we have a bit of a refreshed memory on them now. What I want to talk about next is some of these relational rules for powers. So if I have something like 4 to the power of 3 all over, or 4 to the power of 2, if I wrote that out the long way, I'd have 4 by 4 by 4 all over 4 by 4. Now if I wanted to simplify things, I can see I have common factors top and bottom. I can divide out by 4 and I can divide out by 4, and what am I left with as a final answer? I'm left with 4 to the power of 1, or just 4. What did I end up doing to the powers when I had the same base number? What did I end up doing to the powers? I ended up having 4 to the power of 3 minus 2 was equal to 4 to the power of 1. That's the rule that I'm looking at, the second one down here. A to the power of p divided by a to the power of q is equal to a to the power of p minus q. So you can see where that rule is coming from here. Likewise, I have a rule like a to the power of p in brackets to the power of q. So power in a bracket is going to mean that I end up multiplying the powers. As an example, if I had 2 to the power of 2 in brackets cubed, what would that mean? Well, cubed means I multiply something by itself 3 times. So if I just keep my head and do what I know the thing means, it must be 2 to the power of 2 multiplied by itself 3 times. So how many 2's have I got multiplied together in total? I have 2 by 2 by 2 by 2 by 2 by 2. I have 6 2's multiplied together in total. So what did I end up doing here? I had 2 to the power of 2, and I ended up multiplying the powers together. So, and getting 2 to the power of 6. So we're going to reapply these rules. You have come across all of these before. There's nothing new in that, almost nothing new in that list. So that's all we're going to be doing, practicing this, making sure that we're happy with it. You can see here a to the power of minus p is equal to 1 all over or a to the p. An example of that in practice might be 2 to the power of minus 1 is equal to 1 all over 2 to the power of 1. So if I have a negative power, it means that it changes the line that it's on. Likewise, if I have 1 all over, let's say 2 all over, or 3 to the power of minus 1, that would be 2 multiplied by 3 to the power of 1. The 3 moved up a line because it was negative. So the minus power means that we're going to change the line that we are working on. That would end up being 6. So those are our rules, and we have to be able to use them not just in isolation like that, but in the context of larger problems. So to that end, we can regularly end up with problems like this. We have 25 to the power of 2 over 3. So I have a square root here and I have a cube. So I need to deal with both of them. Usually it's better to deal with the square or the cube, or to deal with the root part first, and then to deal with the power. So make the number smaller first and then make it bigger again. So what is 25 to the power of a half? I'm going to break this up using one of my rules. I'm going to say that this is 25 to the power of a half cubed. This means exactly the same thing as this. I'm using this argument here in reverse. So 25 to the power of a half is the square root of 25, which is 5. And then I'm really looking at 5 cubed, 125. So that's how we can solve these problems with numbers. Final number example before we jump into some more algebraic ways of looking at things. If I have 5 over 2 to the power of minus 2, the power is going to multiply each thing in the bracket, just like we can see here. Just so we can see on the bottom. So if we have a over b to the power of p, we end up with a to the power of p all over b to the power of p. So let's implement that. We end up with 5 to the power of minus 2 all over 2 to the power of minus 2. Now I can see I have negative powers, which means that I am going to move the 5 down and the 2 up. So I end up with 2 to the power of 2 all over 5 to the power of 2. So I end up with 4 all over 25. Now, let's look at a little bit of effectively just simplifying fractions, but with a focus on powers, on indices. So I have 3x squared y all to be squared times xy all over 6x cubed. That looks horrible, but it's made up of lots of bits and pieces that I know how to deal with. I have a power in a bracket here, so I'm going to square everything that's inside here. So I'm going to end up with 9 x to the power of 2 and multiply the power by 2 is going to be x to the power of 4. Y to the power of 1 by 2 is going to be y squared. And I still have that multiplied by xy all over 6x cubed. I can multiply this in now. I knew that I needed to do my power first because, again, all the way back to first year, bin this. I'm going to do my indices before I do my multiply or divide. Now I have 9x to the power of 5 y cubed all over 6x cubed. Now there's two ways that I can do this next part. I can look for a common factor top and bottom. So 3 is the highest common factor in the numbers, highest common factor in the letters is x cubed. There's no y on the bottom. So my highest common factor is 3x cubed. What do I need to multiply 3x cubed by to end up with 9x to the power of 5y cubed? 3x squared y cubed and 3x cubed on 2. So I divide out what is common top and bottom, and I'm left with 3x squared y cubed all over 2, or another perfectly valid version of that would be to start with 9x to the power of 5 y cubed all over 6x cubed. Look for what's common, and partially you do this version in your head, but so long as you're clear about what you do with your lines through, you should get full marks for it. So I recognize that 3 is the highest common factor between these, so I divide 3 in, and I get 3 and 2 on the top. I see that I have a common factor of x cubed, so I can draw lines through and put in what the final answers is going to be, or are going to be, and I end up with 3x squared y cubed all over 2. Both will get you full marks. The advantage of this method is that it trains you in how to spot patterns in numbers better. This one is more prone to mistakes, but in very messy sums where you have a huge amount going on, it can be important to be able to do this method. This is what you should generally be aiming for, because it's less likely to lead to errors and is good for spotting common factors or consolidating your understanding of common factors. This is what we sometimes have to do if we have a big sum that would be too awkward to break down into the neater fashion of the first version. But again, all we're practicing now is the rules that we have on page 21 in your log tables, so that when we have to use them in context, they're not quite as daunting. Because if we can spot that it's really just applying this list of rules and keeping our heads and looking at what little bit I can do each time, these questions are very straightforward. But if we see a big complicated problem and go, nope, we're not doing it, then these questions become an issue. So if we can keep our heads, we'll practice them now, we'll keep age 21 open, and we'll be able to get through these problems without too much hassle.